Okay, welcome back. I hope we're having a wonderful Wednesday. Are we having a wonderful Wednesday? A few people, yes. It's about to get a whole lot more wonderful because we're in math class. What could be better? Michael could name like a dozen things without trying. Okay, let's take a look. So we're on page 15 in the packet. Before we get there, just a look at the GCC calendar. We had talked about kind of a weird schedule thing happening. It will not affect this class, but it might affect your other classes. April the 13th is a Friday. It's a week from this coming Friday, but it is a Monday schedule. So your next Friday, a week from this coming Friday, you go to your Monday classes. Okay? Okay. Also, the last day to withdraw from a class with a W on your transcript as opposed to an F is April the 10th. What day is that? Is that maybe Tuesday of next week?
Yes.
Okay, so I'm going to stare at the back wall so nobody thinks I'm talking directly to them. But if you are at all entertaining thoughts of withdrawing from this class, we should have a conversation. So talk to me at some point before Tuesday of next week, because that's the last day to withdraw from the class. And we can play a very specific game where you say, all right, Ian, suppose I get a 75 on the third exam and a 70 on the final. What would my grade be in the class? And I can give you my best estimate. And then you'd have a real good sense of where you are in this class. So if you're at all thinking about that, we should have a conversation before Tuesday. All right? Okay. So our calendar is here. Today is day number 2 on inverse functions. Next class, we talk about quadratic functions. I'm sure you guys know some stuff about quadratics already, but it's highlighted because what else is happening next class? It's our 7th quiz. So that's coming up. It's on the today and the previous 2 classes. Any question about Friday's quiz? Okay. So we'll go here to page 15. And remember last class we had some extra time, and so we ended up starting what I had planned for today already. So let's refresh our memories about some of the things we saw. So actually, maybe instead of page 15, we'll jump to page 13 for a moment. And I will highlight just a couple of these important facts about inverse functions. So 2 functions are inverses if they undo each other. And here was an observation we made, is that when you have inverses, the x and the y swap. X goes to y, but then swap them for the inverse and the y goes to x. And that also means that domain and range swap. And this right here was our way of saying mathematically that the functions undo each other. If you start with x and you get sent to some number by your original function f, then f inverse will take that number and bring you right back to the x that you started with. That's what that says. On the next page, we saw a process, step-by-step process to find an inverse function. We worked through an example, and the basic idea was to swap the x and y and solve for the new y, which was that guy. That's how we solve for inverse functions. We'll give you guys practice with that today. And then the last thing that we did was take a look at this kind of complicated function up here at the top. This f of x is x cubed minus plus 8. And we talked a little bit about domain and range, and then we went through our process to find the inverse function. And I think that's the last thing that we ended up with, right? Is that inverse function down there. Okay, so I would like to make a change. I would like you guys to make this change as well. See how it says x cubed plus 8? This is number 4. I would really like it to say x cubed minus 8. Can you guys make that change? And number 4, change that function to x cubed minus 8. That's going to have a couple of impacts on the stuff that we did, not major impacts. The domain used to be from -2 to infinity. It's just going to change to +2 now. We change the domain. Domain is now +2 to infinity. We're on page 15, number 4. Okay, and then a few more changes that I'm not going to write all of them. I'll just write the last one. That x cubed minus 8 changes this guy to a minus 8, changes this guy to a minus 8, minus 8, minus 8, When you move that over to the other side, if it's a minus 8, this now becomes plus 8. You don't need to write down any of that stuff. I'm just going to change it in our final answer. The inverse function, which is the last thing we came up with, is now the cube root of x squared plus 8. That plus is the only change I want you guys to record. All right, so I know that's confusing because we did one problem and then I changed it. It's not a major change, but I've got a picture coming up that I just gave you guys the wrong function here. Okay, let's give a shot. Let's give number 5 a shot. Go to Taylor. Okay, so let's try this one. Looking for the inverse of this function, something that undoes that function. I want to say that intuitively we were able to undo some functions last class. For example, 3x plus 4. Remember we talked about in English, what does this do first to the number x? Multiplies it by 3 and then adds 4. That's what we wrote down here in green. So if you want to undo that, first thing you would do is subtract the 4 and then divide by 3, and that's in purple here. That's subtract 4 from the x and then divide by 3. For some functions, you can kind of intuitively figure out the inverse without going through a process. I don't see it on this one right here on number 5. This is a complicated function. X plus 1 over x minus 1. I would have a real hard time undoing that function just intuitively. So we're going to follow the process. So the first step in the process is to change the f of x to a y. And the next step is to change all of the y's to x's and all of the x's to y's. This is where we just swap the input and the output. And now what letter are we solving for? Solve for y. This is the hard part. Everything before is just replacing and changing and stuff. This is the difficult part, the algebra part. Solving that equation for y. Okay, first thing we'll do, make it look like a fraction over here. This is really x over what? 1. Hasn't changed. You guys like to cross multiply when you have an equation like that? We know what that means. So we cross multiply x times y minus 1. That's the one diagonal multiply equals the other diagonal multiplied. Everybody okay with the cross multiply? All right, again, what letter are we solving for? Solving for y. The difficulty here is that y exists in 2 places on both sides. First thing I'm going to do is distribute on both sides. So we'll take this up here. Distribute the x. What do we get? xy minus x equals, distribute the 1. Doesn't do anything. Y plus 1. Okay, now I'm going to make a choice that maybe is not clear why we're doing this, but it will be by the end. I'm going to take all the terms with y and move them to the left, and every term without y goes to the right. So what we'll do here is move this y term over to the left by subtracting y from both sides. And what term on the left-hand side does not have any y's? Is that minus x? I'm going to bring everything without y's to the right. Add x to both sides. So what happens with these x's here? They go away. These y's over here, they go away. That's what I accomplished. Move the y terms to the left. Everything without a y goes to the right. xy and minus y, they're not like terms. I just wrote it. xy, subtract y. Same thing over here. 1 plus x, not like terms. We just write it. 1 plus x. And here's why we did it. Sam? You could factor out a y. How many y's do you see on the left-hand side? 2. When you factor out a y, how many y's will you see on the left-hand side? 1. That's why we did it. When you factor out y from the first term, x, subtract 1. Again, the goal is to get y by itself. Real hard to do that when there's y's in 2 different spots. This is how you trade 2 y's for 1 as your factor. Now I'm hoping it makes more sense why we did this kind of funny step right here. You get all the terms with y on one side and all the terms without on the other, which allows you to factor out the y because you put all the y terms over there. So everything over there has y in it, and then you can factor it out. And then finally, to solve for y, what do I do to get rid of this? We divide. Both sides get divided by the thing in the parentheses there. So we get y equals 1 plus x over x minus 1. Eric. You can't really. That's a good question. You're looking at this piece right here, right? I just wrote it below, but I'm not saying you can combine them. X, y, subtract y is just sitting there. I just wrote it. You can't move them. You can't mush them together. So I just had to write it down. Okay. And then the very last step, instead of y, what's a better name for the thing that we just found? That's f inverse. So that down there is our answer. This is the inverse function. Okay, so Joe is making an observation here. So first, let me just say, this is about as hard of an inverse finding thing I will give you, but I probably will give you one as hard as that. So make sure you are comfortable with this technique of if you have y's in a few places, distribute, get the y's to one side and everybody else to the other, which allows us to factor. Fine. So what's your observation about this inverse function? Joe says it's the same. Is it the same? It is the same. Okay, it's weird, but it is its own inverse. It doesn't happen very often, but let's do a numerical example. How about I asked you to find f of 2. Plug 2 back into the original. Upstairs we get 3. Downstairs we get 1. Everyone agree f of 2 is 3. If I'm doing things right, what should I check f inverse of? I should check 3, and I'm really hoping to get back to 2. Let's plug 3 into f inverse, which is down here in red, although Joe points out it's the same as what's above. What do I get upstairs? 4 divided by 2, which is 2. Start with 2, end with 2. You can start with any number you want. You'll come right back to it. It's a fluke. It's weird. It's a coincidence. But it is its own inverse. Okay. Let's come down to number 6. We'll go to Sarah. Oh, wait. Hold on one second. Eliza? It's a good question. More than one output for each input would make it not a function. We took the number 2 and we plugged it in and we got 3, right? That's the only output you're ever going to get if you plug in. Yeah. Okay, Sarah, number 6. Okay, so there's a lot of words there. Let me make it clear. I'm going to give you a picture of some function f and ask you to come up with a sketch of the inverse. And it turns out there's a nifty little property that we're about to discover here. So that's all that that says right there. Go ahead, Sarah. Okay, so part A, we're going to list a few nice points that are on the graph of f. That's the curve that's pictured. So for example, when I say nice points, do you guys know what I mean? Like 2, 4 is like you want to pick a point that's on the grid and on the curve. Does that make sense? So can you guys, yeah, pick like a few points that are kind of nice. I see another one up here at 8, -4 and 0 maybe. Looks pretty close. Maybe -5 and 0. So once we've got our points over there, we're just going to list them. So I'll call it -4 and 0, but if you pick a different number, that's fine. So I've got 5 points up here listed. And if I'm thinking about the function f inverse, what do you do with the x and the y? You swap them. So for example, the point -4, 0 becomes what? 0, -4. So can you guys just list your same 5 ordered pairs, but just swap the x and y? That's what happens when you go to an inverse. And then part C says once you've listed all your pairs in part B, just plot them. So plot 5 dots and then try to connect them in some nice way. How are we doing with the plotting points? 5 points and then you connect them. So looks something like that. If this curve that's black is y equals f of x, what's a good name for the purple? F inverse of x. That's what we're saying. I don't know what the rules are. I'm not going through my algebraic process to try to find the function that is f inverse. All I'm doing is taking a graph and coming up with the graph, a rough sketch of what the inverse function looks like. And the idea here is that there's a certain kind of symmetry. Are these graphs symmetric about the x-axis? Like if you flip one of them over the x-axis, does it land on the other one? No. If you flip one over the y-axis, does it land on the other one? No. If you flip one of them through the origin, does it land on the other one? No. Through the origin would take a point up here, send it to the origin, and then keep going the same distance. It's not down there. But there is a certain kind of symmetry, and I've kind of, this is another leading the witness thing, where I draw in this diagonal line. Do you guys see the symmetry over that diagonal line? Just take one thing, flip it right over the line, and it lands on the other point. So what that means is that you go perpendicular to y equals to the line, the diagonal one, and then you keep going the same distance, and then you plot a point. That's what we mean by saying it's got that symmetry. And it turns out this is true all the time. Anytime you have two functions that are inverses, they are symmetric with respect to that diagonal line, which we'll go ahead and label. Y equals x is the 45-degree line going right through the origin. So we'll say again, if I give you the function f, the picture, and I want to look at the graph of f inverse, you just do your best to draw this thing flipped over the line y equals x. Just always how it works. When you're ready, we'll go to the next page. Andy? Okay, so that's our summary there. Michael? Okay, so taking a look at this picture right here, I've got this crazy curve. I've got my dotted line at y equals x. I'm going to ask you guys to, again, plot points. Maybe pick 4 or 5 points, you know, somewhere along here, something like that. And then plot the mirror images, flip them all over the line y equals x, and then connect. Okay, so we plot a few points, just enough to get a sense, connect them in some reasonable fashion. It might be really, really hard for some of us to see this, but that's okay. But maybe something like that is F inverse. How does it look? Some people can actually draw these without even plotting any points. They can just free draw, like by hand. I hate those people, just like you do. Yeah. Okay, I do have a pretty sketchpad thing to share with you with about this. That looks familiar, right? That's exactly the thing that you guys just flipped. I will show the line y equals x. It is there. I will take this point P, so I can move this guy around and it just traces out the blue curve, okay? And if you take this point P and you want to find out where it goes, you go straight to the y equals x and then you keep going, so that point would get reflected to somewhere down here, right? So I'll just hit this that button, and that's where that point is. And if you move this guy, you can see they both move, right? And so the point at the bottom gets reflected there. And so what would I like to do with this pink thing down here? If I want to actually see the whole curve, I kind of want to draw it, right? I want to draw that pink thing as we move all along here and see what it traces out. So there it goes. All right, cheating. All right, so hopefully we got something like that. It's okay? Taylor, what did you say, and Sarah, what did you guys say about the original function? Doesn't pass the horizontal line test, right? We know that the original function does not have an inverse that is a function. And you can see here the pink thing, what's wrong with the pink? Doesn't pass the vertical line test. So the pink is not what? Pink is not a function, which is what the horizontal line test had told us before. Still, it's okay. We can still flip over and get something that isn't a function. I could still call it the inverse. It's just not a function. All right, let us proceed. We'll go down here to number 9. Number 9 is the x cubed plus 8, but you guys remember we changed that? Make it x cubed minus 8. And then we're just going to refresh our memories, some stuff that we had written down last time. The domain of this is all the x's between, it's now positive 2 and infinity. It becomes positive. I changed the sign in here. And so it's actually positive 2 now. Okay, the range did not change. It's all the y's bigger than or equal to 0. And then I need somebody to help me out with the inverse. What was the rule we came up with for the inverse? I changed it to a minus sign, x cubed minus 8. It's the same change we made on the previous page. I'm just trying to be consistent with that new one. Can somebody remind me of the inverse? Cube root x squared. It's now plus 8. We made a change and it changed it to a plus 8. Sorry about that. Okay, that stuff we looked at last time, last class. Okay, we're going to go to Brian for number 10. Okay, so Brian read the updated version, so apologies again. We're changing that plus sign to a minus sign. All right, so in those 3 pictures, is y equals x easy to find? Which one is y equals x? That's that dotted line. Okay, so that one's easy. We'll label that y equals x. Then we have two curves that we have never seen before. You got the kind of like opening cup type thing, and then you got this other guy that's kind of opening to the right. I don't expect that we know which one is which just looking at these, because these are complicated functions we're analyzing here. But one of them is the square root of x cubed minus 8, and the other one is this cube root of x squared plus 8. How are we supposed to know which is which? Well, we did some work last class. We found out that the domain originally was all the x's more than 2, and the range was all the y's more than 0. And you guys look, decide which one of those curves has the domain of all the x's more than 2 and a range of all the y's more than 0. Which one is it? The bolder one. Okay, so let's put this guy as f of x. And you guys can see that this picture starts right there at x equals 2 and then only goes to the right. Yes? There's no more picture to the left of 2. And it also starts at y equals 0. And then where does the graph go? It goes up. Only y is bigger than or equal to 0, nothing below. So that one is definitely f, which I guess by process of elimination makes that one f inverse. And thinking of it in that way, I can start to see the symmetry. I know that f and f inverse, when I picture them, are symmetric over that y equals x line. So looking at f, here's the original graph, and then f inverse. I want something symmetric. Well, you guys feel that like that's the mirror image? But then there's that extra stuff, right? I mean, like what's going on over? Like, why is there stuff out there? It's not symmetric with anything. Can you guys see that should be symmetric with respect to some, like there should be something that lands on this. Yeah, we have to stop there because of the negative and the radical. But if we didn't stop, you guys don't need to write this. But do you kind of buy that that's sort of what it's trying to do? And if I let it do that, then do you buy that now that's the mirror image? So it's only because it's cut off kind of artificially, but it's cut off. So really what I need to do is not allow like all the